We also said that we need to look at the limit from the left and the right when we looked at our graphs. So there's some notation that goes along with this important point. In order for a limit to exist, the limit from the left has to be the same as the limit from the right. And when we do these particular calculations, which we'll see how we do these algebraically, they have slightly different notation than our regular limit. So when we take a limit from the right, notice this little plus symbol next to A. That means when we're approaching a number, we're approaching it from the right. That plus indicates that we're a little bit bigger than the independent value. Now, when we approach a number from the left, we're going to use this little minus symbol to indicate that we're approaching it from a little bit less than the number we're approaching. So for example, in the last one we looked at, we were approaching 2. So that means when we were approaching from the left, we were considering things like 1.9. And when we were approaching from the right, we would consider something like 2.01. So something a little bit bigger and a little bit smaller is what we're talking about when we're talking about these limits from the left and the right. So here, we want to look at what's going to happen if these are different from the left and the right. An example of that would be a piecewise function. So consider the function that I'm drawing below. Consider that our point here that we're concerned about is what's happening at 2. The limit from the left is going to be the y value of this closed point, whereas the limit from the right is going to be the value from the open interval. So these are going to be different because the y values that they're approaching are different. And if the limit from the left is different than the limit from the right, then the limit itself does not exist. Now, you can have a limit from the left exist and a limit from the right exist, but the limit itself, the limit without a plus or a minus, would not exist if those are different. However, if they're the same, then our limit does exist. So we're going to look at some examples of this, how we compute this both algebraically and on graphs, and we're going to start to determine how these limits work. Example 1. Find the limit as x goes to 3 of 9 plus x. So again, the idea that we have to go from the left and the right means we need to be getting closer and closer to 3 from both the left and the right. So in the first column, I've picked numbers that are getting closer to 3 from the left. So I'm going to pick numbers slightly smaller than 3, but that are approaching 3. So 2.9, 2.99, 2.999. So here, we're going to start by plugging in the 2.9 into the given function, and we're going to get 11.9. Now we plug in 2.99, and we get 11.99. And when we plug in 2.999, we get 11.999. So here, the limit from the left, I think we can safely say, is approaching 12. So the way we would write this is the limit as x approaches 3 from the left, because those numbers are a little bit smaller than 3, of 9 plus x equals 12. I know that I'm approaching 12 because every time I get a little bit closer to 3, I get a little bit closer to 12, because every time I add another 9, I'm getting closer and closer to 12. I also, however, have to check what's happening as x approaches 3 from the right, so something a little bit bigger. So I'm going to do 3.1, 3.01, 3.001. By adding in more zeros, I'm getting closer and closer to 3. So when I plug these numbers in, I'm going to get 12.1, 12.01, 12.001. And again, I can see that these numbers are approaching 12 because every time I get closer to 3, there's another 0 before the 1, which means I'm getting closer and closer to 12. So this limit I can write as the limit as x goes to 3 from the right, so with that plus sign, of 9 plus x equals 12. So both the limit from the left and the limit from the right exist. Now, because these two limits are equal, because they are the same, that means that the limit as x approaches 3 of 9 plus x is going to equal 12. Because these are equal, this limit exists, and it's the value of 12. Now let's look at another example where the function is a little bit more complicated and the answer may not be as obvious as the last one. So here we want to find the limit as x approaches 0 of the natural log of 2 plus x minus the natural log of 2, all divided by x. Notice that if you tried to plug 0 in, which we don't want to do because with limits we approach and we never plug in, you're going to end up with a 0 in the denominator. So that means we can't even just plug in to try to figure out what the limit's going to be. So instead, we have to take the same approach as before, where we're going to get really close to 0 from both the left and the right to see what it's approaching. So first here, we're going to take the limit as we approach 0 from the right. From the right-hand side, I'm going to use the values 0.1, 0.01, and 0.001. We always want to get as close as we can, so we don't want to pick integer values because those are actually kind of far away. So things like the tenths place, the hundredths place, the thousandths place are much, much closer to 0. So as we approach from the right, I'm going to take each of these x values and I'm going to plug it into my function to see what the corresponding y values are and hopefully be able to use those patterns to determine what we're approaching. When I plug in 0.1, I get 0.4879. Now here, my calculator only gave me 4 values, so I wrote them all down. You'll have to make a decision when you're doing these types of limits on how to round. If a problem specifies how you should round, that's how you should stick through it in your limit. Otherwise, 4 decimals is usually safe. When I plug in 0.01, I get 0.4988 to 4 decimal places. When I plug in 0.001, which is the closest value I have to 0, I get 0.4999 when I round to 4 decimal places. So I'm feeling fairly confident that the limit as x approaches 0 from the right is approaching 0.5. Those numbers appear to be getting closer and closer to 0.5, and I could try a couple more zeros out just to see, but I'm feeling pretty confident about that. Let's also check what happens as we approach 0 from the left. So when we approach 0 from the left, that means we are on the negative side of the number line. So the numbers I pick are going to be negative 0.1, negative 0.01, and negative 0.001. So again, I'm going to plug these numbers into my function to see what the y values are approaching. When I plug in negative 0.1, I get 0.5129. When I plug in negative 0.01, I get 0.5013. And when I plug in negative 0.001, I get 0.5001. So again, looking at these values, I see that the decimals and zeros are going out further and further, and I feel fairly confident that this limit is also approaching 0.5. So since my limit from the left is the same as my limit from the right, that means that the limit itself exists and that that limit is 0.5. Again, I can have the limit from the left exist and the limit from the right exist, but the limit itself would not exist if those had been different values. We'll look at some examples of that later.